Alright, let's take a look at this. Learning objective 2-1, this is actually a little typo. It should say 2-2. Explain the meaning of the slope of a velocity over time graphs. Look at that. Velocity here. We're working with velocity over time graphs. So V versus time graphs. Not PVT graphs. That's different. That's different. I'm going to just circle this and draw a line through it, because you remember you gotta look at your axes when we're looking at these graphs. But let's first recall that when you measure velocity, you want to think about a camera taking photos of the object every second. 0 Mississippi, 1 Mississippi, 2 Mississippi. And velocity is the change in position between each second. Its velocity is the change in position between each second. Miles per hour, meters per second. We always write that mathematically as the change in position divided by the change in time. How much distance has occurred in some unit of time. Okay, so if we got a changing, you know what, I'm going to change this. Well, let's first think about a constant velocity. That'll make life a little bit easier if we just first think about a constant velocity and graph that. Boom, constant velocity, not a changing velocity. And we always know that objects that are moving faster will have a larger change in their position for each section. I keep saying section. Objects that are moving faster will have a greater change in their position for each second. Faster will have a greater change in their position for each second. Now, here's an object that is moving with a constant velocity. And if you're looking at it, you go, hey, Mr. Rip, look at that. That slope is 0, dude. And if the slope is 0, doesn't that mean that the velocity is 0? Well, that would be true on a position versus time graph, but let's take a look at these axes. This is a velocity versus time graph. This is a velocity versus time graph. And on a velocity versus time graph, if you want to figure out the velocity, well, all you got to do is look at the axes. So at 1 second, this looks like it's got a velocity. I'm going to make up a number. Let's say that's just like 2. And at 2 seconds, he's going 2. And at 3 seconds, he's going 2. So he's going 2 the whole time. And what are our units for velocity? Meters per second. So 2 meters per second is this tortoise's constant velocity. So now we're analyzing this, not position versus time graph, but a velocity versus time graph. The slope of this line, it's still 0, and we could think about what that might mean if we have a 0 slope of a velocity versus time graph. Okay, so we got our hare here, the tortoise and the hare. Here's our hare. We know that the hare is moving faster, so it's going to have a greater change in position each second. It's going to have a greater change in position each second. So it's got a bigger velocity. And if it's got a bigger velocity, then what do you expect? If we go up and over, let's just make up another number here for the y-axis. Let's say that this guy's going like, I don't know, 6. And at 2, the hare or rabbit is going 6. At 3, the rabbit is going 6. The rabbit seems to have a velocity of 6. What are our units? In physics, you never forget your units. 6 meters per second. Kablamo. Okay. Easy peasy lemon squeezy so far. And so looking at these two graphs, which line, blue line, represents the tortoise and which represents the hare? Well, clearly we got Mr. Tortoise here. I'll just call him Tort. And then here's my hare. I'll just call him Rabbitron. Why do I have to make up stupid nicknames? Yeah, you can see the difference between those. And those changes right there, that just represents the distance traveled each second. Okay, now let's look at a changing velocity. A changing velocity. If an object, I just noticed that silly picture right there. If an object is speeding up, then the change in position will change each second, or increase, sorry. Let me do that one more time. Changing velocity. If an object is speeding up, then the change in position will increase each second. Will increase each second. This is called acceleration. This is called acceleration. Love thinking about acceleration. Okay, so again, we're thinking about a photographer taking a photo each second, and from 0 Mississippi to 1 Mississippi, this hare has gone that distance, and then from 1 Mississippi to 2 Mississippi, look at that, he's covered more distance. The change in position has increased. Here's our distance here, and then 2 Mississippi, 3 Mississippi. That distance is getting bigger and bigger each second. So if we have a changing velocity, we're going to see an acceleration. And when we want to measure acceleration, measuring acceleration, the amount of change in velocity is the amount of acceleration. Is the amount of acceleration. Let's use a little better science word here. Instead of saying amount, we'll use precise academic language and we'll say magnitude. Magnitude. Magnitude just means amount. Magnitude of acceleration. So the equation for acceleration is the change in velocity divided by the change in time. The change in velocity divided by the change in time. So we're thinking about that delta there. You have a changing velocity. Now, if we look at the graph of a velocity versus time graph, the acceleration is the slope. The acceleration is the slope. So if we're thinking about slope, the slope of a velocity versus time graph is the acceleration. And there's a symbol that we use for acceleration. It's A. So the slope is A. I love it. So that's all I want you all to think about. One last thing, if you wanted to calculate the, we've just got, let's add some numbers on our axes. 2, 3. All right, let's say that at 1 second, the animal is going 1 meters per second. At 2 seconds, the animal is going 2 meters per second. At 3 seconds, the animal is going 3 meters per second. The slope of this graph, the rise is 1, the run is 1. The slope of this graph would be 1 divided by 1. And 1 divided by 1 is 1. So our slope equals 1. So our acceleration equals 1. Now our units for acceleration are meters per second squared. Those are our units for acceleration. So that is this object's, or this creature's, acceleration. Easy peasy lemon squeezy. So far so good, team. Good work.